All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's actually just jump right into it. Of course, we're in the middle of a topic last time. We started the topic of optimization, the process of making something as good as it can be within a certain restriction. So, or restrictions, perhaps. But usually there's going to be one restriction in a Calc 1 class. So ultimately, we saw that making something as good as it can be can be thought of as maximizing or minimizing something in many cases. So you want to do things like maximize profit, minimize cost, maybe maximize area, minimize surface area, minimize the amount of materials used, things of that sort. But there are always restrictions or constraints, as we call them, which kind of prevent us from doing this to an infinite degree to get the ultimate efficiency. So we want to be able to make the best possible scenario within certain restrictions. This led us to the study of optimization, of which calculus is just one of the games in town. Optimization is much broader than just this, but we are going to look at one specific situation in which the single variable calculus can actually help us out. We saw that led us to 6 steps for which we can use to optimize a situation. Of course, you read carefully, you know that. You draw a diagram to kind of get a handle on the situation, understand what's going on, label it properly. Then you're going to set up 2 equations, so that's something that's kind of new. Normally, we're used to setting up 1 equation, but this time we need 2. We need 1 for each item. We need 1 equation to describe our constraint, 1 equation to describe the objective. Remember, the constraint is usually going to be the thing that you have given, that you would already know what your restrictions are, very usually. So that's going to be the thing that you're told the value that you have, right? So a farmer has 100 feet of fencing. That's a constraint. You don't have an infinite number of fencing. You have 100 feet worth, right? So that is how you would set up the constraint equation, figure out what you're given, the given value, and then use that to use an equation to describe that value. We then need to set up the objective equation. Now, the objective equation is the thing you want to optimize. That is the thing you want to make as large as possible or as small as possible within these constraints. Okay, so you need to describe that quantity with an equation. And normally, the diagram is going to help you with setting up both of these. So that's why a diagram could be important. Once you do this, you're going to realize that very usually your objective equation is going to have more than 1 variables in it, but we're in single variable calculus, so that can't work. So what we do is we solve for 1 variable in the constraint, and we plug this into the objective, right? So we solve for things in the constraint or constraints and plug them into the objective. This gets the objective in 1 variable, so now we know how to use calculus to determine the maximum of that function, which we can now think of it as. The quantity is going to be the dependent variable, and you're going to have an independent variable where you can now maximize or minimize. Now, technically, we always find the absolute maximum or minimum. Usually with this kind of problem, the answer is not going to be at the endpoints because the extremes are usually going to be not physically viable. So you might also, you have, a lot of the times you'll have that the relative max or min will solve the problem. But you always kind of should check in your head at least, would it make sense that the endpoint would be a solution? It's always possible. I don't think there's probably a homework problem that had that. I think I chose it. By the way, the homework for the rest of the semester is already up, just so you know. But there is a problem where it's like you had a length of wire that you're going to cut in 2 pieces, and you're going to make a triangle with one and a rectangle with the other one, and you wanted to like maximize the area of the figures that were created. And I think a problem like that, the solution is going to be to contribute 0 length to one shape and all the length to the other shape. So that's one situation when you're actually doing 2 things, and it's possible for you to choose 0 to go to one thing and and everything to go to the other thing, that's kind of going to be a situation where you'd have the endpoints being the solution. Yeah, James?
Yeah, Professor, I just had a question with regards to the homework.
Yeah.
Would it be possible for us to receive an extension on that? Only because with the rest of it being assigned, it would be due all this Sunday. Would it be possible to have an extension on that?
Sure. But I would definitely recommend you do as much as possible um, up until Sunday, as well as practice for the test. So yeah, I could extend that maybe by a week.
Uh,
Would that be enough?
I would think so. I
So
would say
like
so.
the
Thank you.
ninth.
If that works, thank you. I appreciate that.
Okay. Send me an email reminder because I have so many things I have to remember to do. So yeah, just send me a reminder and tell me, oh, you said you're going to extend the homework, and I'll extend it. I'll move them all to the ninth.
Thank you. I appreciate it.
I have met with some of you in office hours on how to study and where homework would fit into that. So I would at least try to touch on all the homework before the test. But if you don't complete it, I wouldn't worry too much about it. It's much more efficient for you to practice from the practice tests on the website. The homework just is to get you used to the idea, but when you're practicing for a test, so like by like Friday-ish or so, you should do like all the homework that you're ever going to do before the test. And then for the rest of that time, you should be practicing test taking and practice tests and timing yourself and all that stuff. Okay. All right. So let's continue. So there are some weird cases. It's okay, Mike. There are some weird cases in which the endpoints will give you the solution, but it's usually not going to be the case. At the end, part 6, which is important, it's not trivial. Sure, if I gave you an optimization problem, you won't have the majority of the points going to step 6, but some points will definitely go to step 6, 1 or 2, where you have to actually answer the question. Something very specific is going to be required of you, and you need to say what that thing is. Okay? So they might say, what is the area of the fencing that the rectangular fence that the farmer can build? They might also ask, what are the dimensions of the rectangular fence that the farmer can build? And you need to answer specifically the question that was asked, right? So going through that 6-step process will get you to solve any optimization problem that I would give you. But as I mentioned, optimization is a lot broader. We actually did an example. We did that farmer example, where you can see me going through the steps, read, diagram, where the farmer with 100 feet of fencing wanting to build a rectangular enclosure of maximum area. We realize that there are many options, but we want to choose, of course, the best one, given his constraints. So we read it, we understand it's an optimization problem, we got a diagram, we created our constraint and objective equation. We had 100 feet of fencing. This is the distance around the rectangular enclosure. That's a perimeter, so our constraint dealt with perimeter, and we wanted to maximize the area. So the area equation is our objective equation. We got a new objective by solving for one variable here and plugging it into the area, which here, yes, it's a parabola. We could know that the maximum occurs at the vertex, but it won't always be such an equation. You can have something where you don't have some neat little formula that gives you the max or min. So I went through the calculus anyway, so we can maximize it by finding the derivative, set it equal to 0 or undefined. That's the critical points, and we solve for the critical point that we need. We understand here that the endpoints would not work, because if I had like 0 going to the width, there's no rectangle. If I also had all 100 feet going to the width, there's also no rectangle, right? So the answer had to be in the middle. So it's going to be a relative max or min. In this case, it's a max. And we can find that by setting derivatives equal to 0 or undefined. It's never undefined here because it's a polynomial, so we just set it equal to 0, solve for x, you got x equals 25. Now, x equals 25 is not necessarily your answer, right? 6 is where you go and you make sure you answer the question. This particular question asked for the dimensions of the enclosure, right? So you need to answer that question with dimensions. Okay, so you have to say length or width, or a common way to do dimensions of like a rectangle is length by width, with the x is like a multiplication x. If you're doing a box, you can also do length by width by height. So you can represent dimensions that way, or you can just literally write out length equals width equals height equals, and that'll be fine. But yeah, whatever it is, you need to make sure you answer the specific question that was asked. Okay, so now I ask you to go through these problems here. Hopefully you try to crack at it. In the interest of time, I'm kind of going to just do them and you guys follow along and ask me questions if you have them. But for the most part, I'll be going through this solo. And hopefully you guys tried it so you can actually compare what I'm doing to what you got. That's the best way to actually practice. Like I was telling other students, sometimes when you're in class and you're just sitting and you're watching me do something, it's going to seem easier than it really is. And it's going to seem like it's going to make sense. That's just because I know what I'm doing, right? I'm the teacher. So you have to be careful, right? I'm sure Michael Jordan makes slam dunking look easy, right? But it's not. It's not easy. Just because you watch someone doing it doesn't mean you know how to do it. That's very important. So hopefully you actually tried these on your own, and you're not just having me solve all the problems for you. That being said, let's actually get into this finally. In terms of timing, I would say optimization, anywhere from 5 to 10 minutes is how much you should be spending, maybe an average of 8. Like I said, curve sketching, you probably spend like 15 minutes on that. Related rates is probably another 5 to 10. And yeah, exponential growth and decay, I would expect like 5 minutes or less. Those problems are easier. So just in case you're practicing and you're wondering, am I doing well enough on time? That would be a rough judge. As far as word problems go, I would say, yeah, like less than or equal to 5 minutes for an exponential growth and decay, 5 to 10 minutes for optimization and related rates, and 10 to 15 minutes for a curve sketching problem. The curve sketching problem is going to be the longest problem type. Okay. Let's actually get into it. Design an open rectangular box, which means you need to tell them how to design it. That's a fancy way of asking for dimensions. It's a posh way of asking for dimensions. When you want to give them a design, you have to tell them, oh, build this length and this width and this height. With square ends, so the left and right side are squares, having a volume of 36 cubic inches, so right there, that's a given. That should tell you that's a constraint. And of course, cubic inches, cubic inches tells you that the constraint is volume, right? Volume is measured in cubic units. Right? So we're reading very carefully, we're picking out the information, we're synthesizing the information. Sure, you can read through the problem once very quickly to just kind of get the gist of it, but then when you want to read carefully and start picking out what you're going to do, notice here that you want to minimize the amount of materials required. That is, this is the objective. Now minimize the amount of material. So you want to build a rectangular box that's going to have like flat sides. Minimizing the material, you can think of this as minimizing surface area. Okay. If that wasn't obvious before, I just told you. So now you just know from now on. one way you're going to minimize stuff is just to minimize the area or the volume that that thing takes up. So you minimize the area, you'll minimize the amount of material because, you know, we want to save the earth, all that good stuff. So this is an optimization problem. Those are the information. So now let's actually get into it. Once we know it's an optimization problem, there's 6 steps, always in a certain order. 1, we of course read. 2, we're going to do our diagram. We're going to properly label said diagram. So diagram is a box and it's open, which means there's no top, right? We're also told that it has square ends. The left and right side are squares. So that means when labeling, I would want to use the same variable to label the left and the right. Whereas the front length, I would call it something else because we weren't given any information on that. So, you know, so that's the left and the right side. So that's our diagram. So now we move on to step 3, where we want to find our constraint equation and our objective equation. So we know the constraint is volume. Volume must be 36. We also know what the volume of something like this is, length times width times height. This means that your x squared y must be 36, right? That's your constraint equation. Moving on to the objective, we want to minimize surface area. So we're going to build up the area equation. And there are going to be several parts to this. In fact, there are 5 parts to a box with no top. So there's going to be the left side, the right side, the front, the back, and the base, right? So the area of the left side, well, it's a square. So it's length times width, it's x times x. The right side is the same thing. For the front, that is this part here. That you'll see length times width is x times y. For the back, that is this part here. Again, you'll notice that that's another rectangle, x times y. And then the base, that's this guy right here. Again, you'll notice it's another rectangle, x times y. Right? So the diagram kind of helps us to kind of visualize the parts that we want to put in. So here you would get area is 2x squared plus 3xy. And that is our objective equation. Now, of course, that's not super usable. So the 4th step is to find a new objective by using the constraint to help us. So we know that x squared y equals 36. This means that y is equal to 36 over x squared, right? Now, it's important to know that there is no real requirement to solve for a particular variable. Could solve for either variable. Of course, you choose the easier one. Solving for x. If I were to solve for x, I would end up introducing radicals. So that just, it kind of makes things a little bit more complicated, right? Now I'd have to deal with fractional powers. Come on, who wants to do that? So solving for x would introduce radicals. So we solve for y. Right? just to make our lives easier. There's no reason why we have to solve for y. It was just easier for me to solve for y. So now I can plug this into the objective. So now my a is going to be 2x squared plus 3x times y, which is going to now be 36 over x squared. So now that basically means my new objective is 2x squared plus the x's would cancel. So this is 3 times 36 over x. Right? Now that's not a parabola. We don't have a nice little formula for that. So calculus is definitely the way we want to go here. 5 now, we're going to want to optimize, right? So you're going to want to maximize or minimize. In this case, we want to minimize, right? So what you're going to do here is you're going to set a prime equals 0 or undefined. So this means you want to, this is going to be 4x. The derivative of 1 over x is minus 1 over x squared. Remember that. So this is minus this constant over x squared equals 0 or undefined. Now, undefined, we would reject because it's undefined when x equals 0, and there's no box here. So you reject, I reject you, sir. Right? Doesn't make sense for the undefined part to be a viable solution. So now the only thing left is to actually solve for where it's equal to 0. We can do this several ways, but one way is to just move that to one side, multiply both sides by x squared, and then divide by 4. And 4 goes into 36 9 times, I think. Right? So now you just have x cubed equals 27, which means that x equals 3, cube root of 27. That's our x. All right, now we get to problem 6, where we're going to answer the question. Okay. Now remember, if there's just one answer, that's the answer.
Hello. Hi, David. How are you?
Just assume this is the
I'm
answer you
good.
want.
Thank you so much for giving me a call.
The only way I'd recommend testing in a class like this is if you have several possible answers and you want to choose one among them, then you might have to do some sort of test to see who's really giving me the minimum versus the maximum. But now we want to answer the question. So we need a design, which means I need dimensions, which means if x is 3, then I need to know the y to give you the full dimensions. Y would be 36 over x squared, which is 36 over 9, which is 4. So this means dimensions are, it's a 4 by 3 by 3 box. Right? So the square sides has like 3 inches by 3 inches, and the other length is 4 inches. If it was inches, I don't even remember. But yeah, don't even care about the units here. So that would be the best design for the box. Such a box will hold 36 cubic inches, it would also have the minimum amount of surface area, which means you'd need the minimum amount of materials. There are many boxes you could build that would have would hold 36 cubic inches, but their area is going to be bigger than that, larger than this box. Okay. So that's that. And again, 6 steps: read, diagram, constraint equation, objective equation, find the new objective, maximize or minimize, answer the question, always. Okay, so with that being said, let's actually get through the rest. Okay. So here is another optimization question. Notice that we have a rectangular corral of 162 square meters. That's given. Come on, iPad. That's given. So this is your constraint. You'd also notice that it is square units, so that's area. Right? It's to be fenced off and then divided into 2 sections as shown in the figure beside it. Find the dimensions of corral so that the amount of fencing is minimized. So here we want to minimize fencing. This is the objective. We want min perimeter. And what do we want? We want the dimensions. So this is the Q that needs to be answered. Okay, so we're constrained by area. We want to minimize the perimeter, and I need to tell you the dimensions that would satisfy that, assuming that we're building a corral of this type. So obviously 1, read. 2, diagram. So we were kind of given the diagram, but let's actually just label it. Labeling is going to be important. So what I'm going to do is I'm going to call this length X. I'm going to call the vertical length Y. I would mention here that you could also label as something like X is half that, and that is X, and then that is Y. But you see, that would make this length here 2X, and that's just, to me, needlessly complicated. All right, but to be fair, it's not wrong. But I see whenever I give a diagram like this, students tend to think that they have to think of one side of half of the fence as different from the other half of the fence. You don't. So you could do it this way, but of course, my X is going to be actually double your X. But as long as you state the right dimensions, then it won't matter. Also, we don't even know if it's split in exactly a half. It's not going to matter. Also, we don't actually know it's split exactly in a half. Doesn't matter anyway, but it just, as a concept, when you're setting it up, you're already making some sort of assumption that you weren't given. In general, you don't want to do that. You don't want to assume things that you're not given. Doesn't matter here, but generally, you don't want to assume things. Not given. Right? So you'll look out and you'll actually get the right answer here, just with a different proportion than I do. But generally, you don't want to play that game of just pretending that you know exactly how this person wants to divide the fence. You don't really know. But yeah. In any case, I would go with my labeling because it prevents me from using that 2. Why is that 2 there? So this leads us to 3. We're going to find the 2 equations. So we're going to find the constraint and the objective. So the constraint was the area. So I know this tells me that x times y is 162. Whereas with you would have 2x times y is 162, and then you'd have to divide by 2 to get the x times the y. So it's just kind of weird. Objective, though, objective is perimeter. Now, how can we define perimeter? Well, it's the length of all around. You should, of course, notice that this length here is also going to be y, so will that one. And this length here will also be x. It's a rectangle. So we have 2 x's and 3 y's. So that's my objective. That's my constraint. 4. We're going to need a new objective. So I can solve for any one. So let's say solve for y. Sometimes the coefficient, one is a 2, one is a 3. Sometimes the bigger coefficient, you want to solve for the other guy because you don't want to have to deal with the bigger coefficient. But 2 and 3, they're pretty close. I don't see much point in discriminating against one or the other. Here, then our p would be 2x plus 3 times the y. So that's our new guy. So now 5. Want to maximize or minimize? And in this case, we want to minimize again, looks like. Amount of fencing is minimized. Either way, it doesn't matter. I'm going to find the derivative. Derivative of this is going to be 2 plus, or 2 minus, rather, 3 times 162 over x squared equals 0, or undefined. For undefined, x equals 0, of course, reject. Doesn't make any sense. For this, though, we would have 2 is equal to 3, 162 over x squared. This means that your x squared would be 3 times 162 over 2. You would get 2 goes into 16 8 times. 2 goes into 2 1 time. So it's just 3 times 81, which we know is 9 squared. So x is going to be plus or minus the square root of 3 times 81. Of course, we're going to reject this because you can't have a negative sign. So this means that your x would be 9 rad 3. There's only one answer. We're just going to assume that's the answer and move on to answering the question. So that's step 6. So we want the dimensions. So we know that x equals 9 rad 3. We also know that y is equal to 162 over x. It's 162 over 9 rad 3. 9 goes into 16 1 time, remainder is 7, and goes to 72 8 times. $18 over rad 3. So you get dimensions is 9 rad 3 by 18 over rad 3 meter fence, where the divider is of length 18 over rad 3, because the divider is the y. So you want to just identify which one of the length is going to be the divider. So that's that. Here's another problem. A cylindrical can without a top is to be made to hold 8,000 pi cubic meters of liquid. Find the dimension of the can that will minimize the amount of material needed to make the can. That is minimize the surface area of the can. By the way, that statement right here, Jhevon probably wouldn't tell you that. I'm going to expect you to know that area is what you want to minimize. But other than that, we know that this guy here is a constraint. We know we want to find the dimensions, that's the Q, and we want to minimize the amount of material. So we want to min, that's our objective, min surface area. Okay. So go through our 6-step process. 1, read. 2, diagram. It's a cylindrical can. So we can talk about the height, which is h. And it'll have a radius, of course. and it's open. Okay. Now let's go with step 3. So we need the constraint equation, and we need an objective equation. I don't know why I wrote out equation here. So the constraint equation we know is volume is the constraint. We also know that the volume of a prism is the area of the base times the height. So this means we know that volume equals 8,000 pi cubic units. This means that pi r squared h equals 8,000 pi. Or in other words, r squared h is just 8,000. So that's our constraint. The objective is a little bit more tricky, but I'm just going to tell you what the trick is here, quote unquote. How you find the surface area of a can. Turns out you can break a can into components. So what you can do is you can actually cut vertically. And unfold this, right? You'll realize that the can is made up of, this can in particular is made up of 2 parts. Where I can slice one and start to unfold it. And then there's going to be the base. There is no top. So that's the side and the base. And it turns out that the sides of a cylindrical can will actually unfold into a rectangle. So this, you'll notice that it'll completely unfold into a rectangle. Now, of course, the height of that rectangle is going to be the height of the can. And you'll notice that the distance along the length is the distance that was wrapped around the base. Right? That was what was wrapped around. And so that length has to be the circumference, 2 pi r. And then we have another component, which is the base of radius r. So this tells us that the area is going to be pi r squared, that's the area of the base, plus the area of the side, which is just a rectangle, length times width. So you would have 2 pi r h. And that's our objective equation. Okay. So now you know that trick. You don't have to draw these extra pictures, but I wanted to explain to you where this formula was coming from. You'll just realize, oh, it's going to be a rectangle combined with a circle. And so you can get the area that way. So now we are on to step 4, where we need the new objective. And so that's going to be, we know that r squared h is 8,000. This means that your h is 8,000 over r squared. This means you can find your area to be pi r squared plus 2 pi r h. So I'm going to plug that in here. (8,000 over r squared). So you would get that the new objective is pi r squared plus 2 times 8,000 pi over r. Moving on to the fifth step, you want to maximize or minimize. Here, once again, we want to minimize. We are going to then set a prime equals 0 or undefined. This means 2 pi r minus 2 times 8,000 pi over r squared equals 0 or undefined. Undefined means r equals 0. Of course, you reject that possibility. For this one, you would have 2 pi r equals 2 times 8,000 pi over r squared. Could multiply both sides by r squared, get r cubed, and divide both sides by 2 pi. Of course, 2 goes into 2, pi goes into pi, so you get r cubed equals 8,000. This means r equals the cube root of 8,000, which is 20. Okay, so you get r equals 20. Now, of course, step 6, I'm going to answer the question. So we need the dimensions. We know that r equals 20 is the radius. So this means that h, which is supposed to be 8,000 over r squared, which in this case is going to be 8,000 over 20 squared is 400. That's going to be like 80 over 4. So that's going to be also 20. That's the height. So your dimensions would be radius is 20. And height is 20. That being said, I want you to try this for next time. Tell me what you get. We're going to finish optimization, which is the end of chapter 4, which is the end of the derivatives part of this course. We're going to start talking about the other part, integration, which, yeah, I know it seems like, oh, we spend the entire semester on like limits and derivatives and we only have a little bit for integration. That's normal. Normally, integration is really studied in Calc 2. But they just kind of introduce you to the concept in Calc 1. So that's what we'll be doing for the rest of our time here, talking about the other problem that calculus is meant to attack, the area problem, and the the solution to the area problem, which is the integral. We'll start talking about that tomorrow after this example. So be sure to try this one. This is a nice example, kind of nice for a test problem, maybe even a final problem. So definitely try to see how well you do on that. And I would also time yourself on how to do that. So you want to aim for 10 minutes or less. I doubt you can get it in 5 minutes, but if so, awesome. But try to get this done in 5 to 10 minutes, and we'll pick up with that tomorrow. So, all right, that's it. Thank you for your time and attention. I remember to extend the homework, so I'll probably do that right now. And it's on James. If the update, he does see the update, he'll email me. So, all right. Have a good rest of your day. I will see you guys tomorrow in the next one. Ciao.